before we proceed. So, so we solve G space of I, and here my G was UN. We talked about a G space Li that had this cohomology, invariant cohomology, was the Hochschild homology of these D, DSI, Bose-Samuelson chain complexes. There was an observation that Li supported this map to G mod mod G under the adjoint action, which was equivariant. This was my notation for equivariant maps. And then we asked the question is, okay, well, besides singular cohomology, singular equivariant cohomology, what other cohomologies can I evaluate on this object using this structure here? And the observation that we made is that one should think of this as a local system, maybe a derived local system. In other words, that I want to think of G as B of the affine Grassmannian, which is not a discrete group. So you know, there's higher homotopy here. Even so, one should think of this as the classifying space of the affine Grassmannian and think of cohomologies that support an action of this, and that will allow you to twist the cohomology of this. So this is a general philosophy. And our example of such a cohomology, twisted by loops G, and remember my G is some UN is loops U infinity times HZ. So this is equivariant singular cohomology, and I'm just taking a direct limit with n so as to get. So this guy has an obvious action just by left translation by this group. Yeah.
Sorry, just to clarify, what are we thinking of as a local system on what?
So I have a space. So just like the usual way of thinking of local system is I have a topological space and a representation of the fundamental group of it in some group. So here I'm thinking of a space mapping into this. And what you can do if you want to think in terms of that is take the loops on this map. And that would say that the loop space of this, which is sort of like the fundamental groupoid, if you will, have a map to loops of G. So it's a derived version, not a discrete. Neither of them is discrete, right? So that's my local system. Make sense?
I guess what? So it's a local system on
this space.
On Li?
Yeah. So so let me generalize the statement. Let me answer your question perhaps in a better way. So this was the theory that I would want to take in if Kovanov homology was relevant. And we observed that the homotopy groups, and maybe we call this script H, the homotopy groups of script H are just the equivariant homotopy of this with some parameters. So really one wants to think of formally so let me consider the power series bi x to the I. So it's a formal power series. You want to think of this as a universal twisting class. This formal power series universal twisting class, and I could set the parameters to whatever I want. And for Kovanov homology, and I screwed up the degrees here, for Kovanov, SLN link homology, we set B0 equals B sub n equals 1, and all the other BIs to be 0. And that's the twisting, that's the specialization that will end up giving you Kovanov homology when I apply the twisted homology to this and then take that chain complex and its homology. And so what I should have said last time is that these are the variables, these are the twisting variables that correspond to that differential. And now I can see how to think of the right differential, because these guys suitably, or rather these powers, they transgress into the cohomology of the unitary group, the classifying space of this. And so the right class would be D2n plus 1. So D2n plus 1 would be the odd class in the cohomology of the unitary group that you would flag to calculate the differential like we talked about last time. So this is just to set the record straight. What one should think of, this is the power series that sort of is a formal power series which has all the twisting parameters. People who work in the world of matrix factorizations think of this as the derivative of their potential. So there's an object called potential in matrix factorizations. And this power series is what you would or should think of as playing the role of the derivative of the matrix factorization, of the potential for the matrix factorization. Okay, and then, so Dan asked the question, what if I take instead of this theory, equivariant K-theory? Because equivariant K-theory is also a theory that supports a twisting by this. In fact, those are the only two interesting theories I know that support twisting by this. In other words, have an action of the affine Grassmannian on the theory. So for equivariant K-theory, has twistings indexed by the natural numbers. There's one twisting for every natural number, and I'm assuming G is, maybe I should have taken it to be semi-simple. But let's not worry about the fact that G is not semi-simple, has one extra circle in there. Essentially, the twistings are indexed by the natural numbers. And also, let's make believe I can apply equivariant cohomology to all of these things. Nothing stops me from doing that and then calculating the chain complex, because of course we had that chain complex set up on the level of equivariant topological spaces. So I could, in principle, apply any cohomology theory. I might not get a link invariant, and there's an algebraic condition to check that I mentioned last time, but I can certainly calculate the chain complex. And so I can make believe that I have a link homology theory based on K-theory instead of this cohomology theory. And if I believe that, let's just calculate its value on the unknot, right? Just the circle. For that, I would want to calculate a U1 of U1 crossed over U1, U1. Remember, this is my L of the empty set when n equals 1. Right? We talked about this being the object that you should look at the twisted cohomology of to calculate the SLN or the corresponding cohomology for that twisting. And I'll put a little n here to indicate that I'm taking the twisting corresponding to the natural number n. You sit down and work this out. In fact, this was done a while ago, and this is all implicit or maybe even explicit in work of Dan and Konstantin and Mike Hopkins. This turns out to be this. Turns out to be this ring. Again, there's that shift by 1 that we saw last time. Remember when we were calculating this for the cohomology theory script H, I mentioned that there was a shift by this class Y that shifted everything, and you had to normalize that. Something similar happens here, but ignoring that shift, this is the answer you get. So it looks like some deformation of Kovanov homology or SLN link homology. I remind you what the SLN link homology is. It wants to be this. So people who work with link homologies do have a homology theory, at least characteristic 0 that has this as its value in the unknot. It's called Lie homology. It's not terribly interesting from the standpoint of invariance of links. It loses a lot of information. There's a spectral sequence that starts off with Kovanov homology abuts to the Lie homology, but loses a lot of information. It is important when one talks about applications to gauge theory. There's something called a Rasmussen invariant that relates the fact that there's a spectral sequence starting here, abutting here. But I wanted to point out something interesting about this. If you look at the work of Dan and Konstantin and Mike, there's a very canonical identification of this guy with the level n representations of LU1. So Graham talked about positive energy representation. So there's this class of representations for the loop group, and I'm thinking of the simplest one, U1, and I'm thinking of the level n representation of U1. And if you look at, so it actually turns out to be a non-trivial fact that they actually form a ring, Berlin algebra. And if you look at the Grothendieck ring for those representations, for the level n representations of U1, you get this. And there's a very clear identification of this with the Berlin algebra. It's a geometric identification. So let's make a very interesting observation. Level n representations of U1 is what happens to be the deformation of SLN link homology. But if you were working with quantum groups, you'd see everything upside down. You'd say you want the level 1 representation of SLN to end up corresponding to this, or potentially this. So I just wanted to illustrate this to point out that there is a level rank duality that you can't get around with this picture. So, you know, you get the right homologies, you get the right link invariants, but things get turned upside down. And I don't know why, but I get the feeling this is somehow a version of Schur-Weil duality, but I can't make that statement precise. So anyway, that's what I wanted to point out. And maybe there was a question somewhere? Yeah.
Just remind me what the H sub Z was.
That's just singular equivariant cohomology. Just, you know, your equivariant cohomology. So you take a space, and if you want to calculate a G equivariant cohomology, you just take the homotopy orbits with respect to G that we talked about last time, and then do the singular cohomology. So that's what I wanted to mention. I wish I had spent some time talking about that last time, but like I said, it takes me 24 hours, and it's an ugly process.
You mean like twistings in this general context, and is it related to what is usually called twisted cohomology?
It is, I don't know many definitions besides the one definition of twisted cohomology. Yeah, you need a situation like this where you're, so you know, twisted cohomology. So in my context, so it's a functor from spaces with maps to this. So it lives on this kind of data. The moment I'm given a map like this, I can take one of these twistings for K theory and calculate this. So it's a functor from a category of spaces with a G action and a map to G mod mod G into actually modules over regular equivariant K theory.
That's a twisting.
This is twisted theory. This is the twisting. So the twistings are classified by, I mean, there's an integer's worth of twistings, and for each one of them, you can calculate twisted cohomology, and that is the twisting you fix. Yeah, but it's a functor on such objects, and it happens to be a module over usual cohomology, which I can think of as zero twisted cohomology, if you will. Okay, so now let me continue. I had promised you that I will construct a global homotopy type, an equivariant homotopy type for these spaces Li, and not just say that these Li's fit into a chain complex by restrictions, which do exist. Let me put all of that together in the following way. So recall, L sub I, I'll draw a picture. So here I was a multi-index, I1, I2, Ik. My G is secretly UN, N is the number of strands of my braid. So for this, the picture that went along with it was this picture, right? X1, X2, XK, and this is GI1, GI2, GIK. And at all these points, I also noticed that LJ sat inside Li, and the way it sat inside Li is just I included T inside the corresponding G's for the indices that are missing in J, right? So I would get something like, imagine I got something like this, but this moduli is no different from the moduli where I just shrink this to a point. So shrinking to a point won't change anything. So those were the pictures. So what I'm now going to do is going to systematically remove these guys. So I think of these in the picture that I will describe today, hopefully. I want to think of these as transparent bundles that really don't have any GI dependence at various points, right? They're just a torus. So you could just collapse these two and forget the fact that there ever was a G over there. So they're transparent in some sense. And I want to systematically remove all the transparent defects from Li to get something that's pure, in the sense it's strictly something that sees all of these groups, right? It does not have any redundancies of the maximal torus sitting inside it. So I'll do that in a way that homotopy theorists like to do a lot. I will start pinching these subspaces out of this systematically. And when I say pinch, I mean in a homotopical sense, there are two things you can do. If you have a space and a subspace, you can just simply take the quotient space by killing that subspace. That's a bad thing to do. What you really want to do is take the cone over that inclusion. So that's the right way to think of a quotient. And so you have a space, you have a subspace, and you take the cone over that inclusion. If you think of it as a cone on the inclusion, then the original space is a subspace of the cone, right? So what I'm going to do is I'm going to start off with this guy and start coning things off. So this will be the lowest piece in a filtration. But then the final piece should really be thought of as a quotient of this. But as I'm going to set it up, it'll just increase in cells. So it's going to get bigger and bigger as a topological space. Here's what it is. So I'll just say it. So here's my plan. Construct a filtered G equivariant space, and I'll call F dot for the filtration and S for strict Li. Strict just going to mean that I'm just going to get all the pieces that I want with no redundancy. And it's going to be a filtered object. So F0 of my strict Li is just going to be the guy before the original guy. And what I want to do is I want to think of that as a co-fiber sequence where I've pinched nothing out. I took my Li, the empty set maps into Li, so I have not pinched anything out. You want to think of this as a co-fiber sequence, okay? Meaning that this thing with nothing removed gives me this. Now I'm going to include this. So this F0, and I want to make F1. Here I'm going to remove all the J's that have length k minus 1. So this, so maybe I should just here, I'll take Li, this is just the identity map, and I'm going to take the union of J, which is k minus 1, and J not, this is. So this diagram clearly commutes. What have I done here? I've removed all the J's that have one redundancy. They have a redundancy at one spot. So these are length k minus 1 guys. So pinch them out. But of course, in doing this, you notice I've pinched too much out because there's intersection between two J's, right? There may be things where two of the redundancies are missing. They may be, so I need to accommodate that. So there's an inclusion-exclusion thing going here. So same Li, remove more. This is Lj. So I hope this is making sense. What I'm doing is I'm removing more and more things of smaller and smaller length all the way up to I. And then Fk is going to be the final one. So it goes all the way up to Fk. And that's where everything stabilizes. So Fk is just Li with all the J's removed all the way from the empty set up to length k minus 1. So at every stage, I'm coning off more and more things. So this guy sits inside this guy, sits inside this guy, but homotopically, you want to think of each of these steps as quotienting out more and more things. So this is just a construction of an object. You want to think of this as the filtered UN equivariant object that, has systematically removed, systematically is the word here, removed all the redundancies, all the transparencies. So what's this guy's claim to fame? It has a natural filtration, obviously. By construction, it has a natural filtration. And if I look at the rth filtration and I quotient out the R minus first filtrate, all I'll get is a veg of all the J's, which are of length n minus R, the R-fold suspension of Lj with a disjoint basement. So it's a filtered object, and each associated gradient kind of looks like we want it to look. Now, whenever you have a filtered equivariant object, you always have a spectral sequence. You have a spectral sequence that converges to the direct limit or the union of these spaces. And its E1 term is just the cohomology of these guys. So there is a spectral sequence converging to the equivariant cohomology of Fk of SLI with E1 term, basically the chain complex we had before. It's just given by direct sums of the various J's of the various steps. This is the chain complex we talked about last time. Is any questions here? The one we've always talked about, the one that Kovanov had to categorize his link invariants. That's the exact same chain complex that you get because of this associated graded property. The homology of that chain complex is a link invariant. In fact, all subsequent terms of this spectral sequence are also link invariants. So theorem I for I bigger than equal to 2 are all link invariants, homological link invariants. What link? Basically, the link that corresponds to equivalence class of sigma I. That's the link. By Markov's theorem, each of these equivalence classes is a link. And if you look at this spectral sequence, its E2 term is by construction, Kovanov-Brozonsky triply graded link homology. But the claim is that every subsequent term of the spectral sequence, E3, E4 on all the way down, are also link invariants. Now, this has been studied from an algebraic standpoint. Rasmussen has studied these things in characteristic 0. And there are conjectures out there, and I don't know the status of where these conjectures stand. I believe they have not been settled, that there are no differentials between E2, E infinity. There's only one extra differential that gives you E infinity. So the cohomology of Fk, which is the stabilizing value of this system, is achieved by one extra differential that happens on Kovanov-Brozonsky triply graded link homology, in characteristic 0, and then everything just is what it is. The value of this guy is not terribly interesting. This space, this is sort of an interesting phenomena that occurs here. You have a spectral sequence that converges to something not interesting. But what is interesting is its E2 term. And possibly the last differential that goes from the E2 term to the E infinity term. So clearly that differential retains some amount of information. And that information is the relevant structure here. So if you think of this space, what have I really done? I've pinched out all of these things, and you can think of that object, the direct limit of having pinched everything out. If you think about what I'm actually doing, I'm actually just thinking of a Thom space. There's a representation of the torus whose Thom space is this space. Okay, so this is the structure of a Thom space. So Thom isomorphism will tell you that the UN equivalent cohomology of this is more or less the cohomology of a subtorus. So it's polynomial algebra up to a shift, a Thom isomorphism on some number of variables. Is there a question? All right. So I want to say that this filtered object is in and of itself a link invariant. So what we have is not just a filtered object that recreates these algebraic link invariants, it is itself a link invariant. And in what sense is it a link invariant? So let me introduce what the equivalence classes would have to be. I mean, it's too naive to say this object just as is a link invariant. What you would have to do is to say this object in some set of equivalence classes is a link invariant, because that happens algebraically as well. So, so here's a theorem. SF, F dot SLI is an invariant of the link given by the closure of the braid up to quasi-equivalence. So I'll have to explain what that is. So let me define that. So I'm claiming that this filtered object lives in a certain category where there's an equivalence, and that up to that equivalence, this is an invariant. So two filtered G spaces. Sorry, I'm going to add something here. Doing this on purpose. I'm using the word spectra because this is the first point in time where I can't avoid the word spectra. Because I want to have an object where I can add and subtract maps. And I can't do that for spaces, right? If I have maps into two spaces, I can't say here's a sum of the two maps. So I want to do the least possible thing that I could possibly do to spaces to get an additive category, and that's spectra. So spectra is a sort of the natural, the canonical, the obvious, maybe the universal thing you could do to create a category that's additive that contains a natural map from the category of spaces. And here we're working with equivariant spaces. But it's really not, you don't have to know what a spectra is if you trust that you can, it's a category where spaces, equivalent spaces map, or even filtered equivalent spaces map. And if you have two maps, you can add or subtract. That's all you need to know about that. So two filtered spectra, let's say F dot and G dot are quasi-equivalent if they are connected by a zigzag of elementary quasi-equivalences. And now, of course, I have to tell you what an elementary quasi-equivalence is. An elementary quasi-equivalence is simply going to be a map whose fiber in the category of spectra is acyclic. So F dot between F dot and G dot is an elementary quasi-equivalence if it's fiber or cofiber. So in the category of spectra, fibers and cofibers are related to each other. Just the cofiber happens to be the suspension of the fiber. So if it's cofiber or fiber, is acyclic. Let's call that fiber Z dot. And what does it mean for Z dot to be acyclic? It just means that the associated graded, so if I have a filtered object, I can look at its associated graded, and I'm claiming that there should be so a homotopy going backward, so that boundary H plus H boundary equals an equivalent. So you have a fiber, it's a filtered object, look at its associated graded. The associated graded in the category of spectra will form a chain complex. It's again comes from the fact that spectra is an additive category. And I'm asking for that chain complex to be acyclic. Again, all of these words make sense. You don't have to have a linear category to do this because I'm allowed to add and subtract maps. So it makes sense to say that there is a homotopy so that boundary H plus H boundary is an equivalence. The equivalence of the 8th term. So it's what you would have expected for a chain complex. A chain complex is acyclic if, it's homotopy trivial if there's a homotopy backward so that, the commutator, the supercommutator with the boundary is an isomorphism of that given level. So that would make the whole complex trivial. So I'm making exactly the same statement about the fiber or the cofiber using the fact that I can add and subtract maps. So that definition follows through. So this is what an elementary quasi-equivalence is in my category. And now a quasi-equivalence is simply a zigzag of, so two things are quasi-equivalent if, you can create a zigzag. from here to here of elementary quasi-equivalences. Now, if that is the case, then I claim that, so meaning if I set that equivalence relation down, then I claim that this filtered object that I have over there is a link invariant. And the exact same statement works for a construction where I don't take coaxial homology. So instead of LIs, I were to use BIs. Remember the BIs, the Bott-Samuelson guys? Those are the ones that categorize braids, not coaxial homology of the braids. And so I would make the same construction, exactly same construction, by pinching stuff off. And then I would have a theorem of the same kind in that framework as well. Okay, so this is where I want to stop here and take the last half hour to give you, to do what I've never done in public before, and I probably shouldn't, but it's like making haggis, I assume. All right. Any questions before I move to the TQFT version of everything? Right.
So these other pages, which are also link invariants, what do they categorize?
I don't know. So this thing here, the final guy, this guy here, is just counting the number of components of your link. It's not interesting. Like I said, it's basically all it is. It's a subtorus. Its cohomology after thumb isomorphism is a polynomial algebra and a fewer number of variables. And how many variables do you have? Well, you have as many variables as the number of components of the link. So it's a very weak invariant of the link. And of course, the E2 term is Kovanov-Rozunsky homology, or Kovanov, the twisted version. If you want to do all this twisted, you would have the same setup. So the question is, what happens in between? And I don't know the answer. You're abutting to some very stupid invariant. You're starting with something very interesting, and we have no idea what happens in between. Yeah, it's a conjecture. And like I said, I haven't really followed the literature on what the status of this conjecture is. Maybe the conjecture is that there's one differential that just destroys all the structure. So you don't have anything in between. Yeah. Any other question? Right. Right. So let's put all this together, and now let me digress a little bit. So here's some digression, and I'll get back. So let's say M, so let M be a manifold with a G bundle. So G for now is just some arbitrary compact, maybe connected Lie group. So think of this as a background field. I just have a map from M to BG. That's what I mean for now. Nothing terribly fancy for the moment. It's just a map from M to BG. No connections or anything for the moment. Now, if M had the structure of a product, if M was N times S1, so let's call this map F of M, then you have F of M going from M cross S1 into BG. I can always adjoint this map over. So I get F of, let's say, N. Maybe I shouldn't say N. Maybe call it F hat of N. It goes from, and this is, my apologies, N. It goes from N to LBG, right? So this is just maps from S1 into BG. Just adjointing this over, so I get a map from N to the loop space of BG. Okay, so let me make a claim now, which is very familiar to some people and maybe somewhat surprising to others who haven't thought about this, is that this object here, LVG, is very familiar. It's just the homotopy quotient of G mod mod G. So let me spell that out. So clean. So I mentioned, I talked about this notation yesterday, and I'll remind you. So G mod mod G is just a conjugation action of G on itself. And I put the H here to mean EG crossed over G. So this just means EG cross G with an equivalence relation, EG G inverse H is equivalent to EH. Sorry, there's a conjugation. And EG was your contractible G space. That was a universal G bundle over BG. So I'm claiming that this guy is equivalent to LBG, and let's do a quick proof. So what is LBG? LBG is maps from a circle into BG, right? Now I can decompose a circle as disks glued together, two circles glued together. So now I have a bundle. So this, I have a map from S1 into BG. So I have a bundle over this, a bundle over this, and they both agree at these 2 points, right? So this is D plus, this is D minus, this is S naught, which is their intersection. So what I have is so this data, I get bundle D plus, bundle over D minus, and they agree on S naught, which is intersection. Okay. So what this is, now what's a bundle over D plus? D plus is contractible. The bundle over D plus is just a point, and when I do this kind of construction over it, or I think of a map from a point to BG, right? Contractible space mapping to BG. Well, how many? What is that? That's just BG. So what this says is I have a map from BG over S naught. I have a map from BG because map from S naught into BG is just a product. BG cross BG. This is BG. This is the D plus. This is the plus. Plus. This is the D minus. And this is S naught. And if you have a bundle over the disk and I restrict it to the endpoints, they're isomorphic. So this is a diagonal map, and this is the diagonal map. So LBG is a pullback, a homotopy pullback, if you will. These are actually contractible spaces. So this is in fact a homotopy decomposition. So that's why you get a homotopy pullback here. So that's what LBG is. It's a homotopy pullback of the two diagonals mapping in here. And now we did something last time similar to what I'm about to do. I'll write this inclusion map as actually a fibration. So I can get a sense of what this homotopy pullback actually is. And that is the so notice, so BG can be written as E of G cross G, with G cross G acting on G by left and right conjugation. So what I'm doing here is that so it's sort of like a conjugation on two sides. If you think of this action, then this G is a homogeneous space under this action. So you can write G as a quotient of G cross G by what? What's the stabilizer of the identity element? Well, it's the diagonal subgroup. So this is E G cross G crossed over G cross G, G cross G over the diagonal. That's what it is. And now I can just cancel this off, right? This is E G cross G over the diagonal. And now I take this as my model for EG. Remember, all you need is a contractible free G space for EG. So that's my choice. Because the diagonal subgroup clearly sits inside G cross G, and therefore it also acts freely on the space and it is contractible. So this is my model for BG. It's an explicit model that identifies this G as a subgroup of G cross G, which is the diagonal subgroup. So that's this map, or you can choose it to be this map. But writing it like this says LBG is this pullback. Here, your G cross G is acting by conjugation on this. And now I'm pulling again back by the diagonal here, which means that this is EG acting on G by conjugation. Because now I'm taking the diagonal as a subgroup of this and then acting by this representation. So I get the actual conjugation action. So what I get is EG crossed over G. G. Yeah, it's the restriction of this along the diagonal. Okay, so that's what I wanted to claim. That's the space. Okay. So let me just write out what I'm trying to say in this. I'm saying background G fields on M cross S1 are G mod mod G orbit fields on, sorry, let me write this out before I screw it up. To conclude, BG or G background fields on N cross S1 correspond to G mod mod G H. That's the conclusion. On N, you get a map to LBG, which I write as the homotopy orbits of G conjugation action. Now you can ask, well, can I get rid of this H? And yeah, the answer is yes. I mean, you could throw some extra structure on this setup so that you could get rid of this H and actually get a map to the stack G mod mod G. What would that extra structure be? It would be a connection along S1. So if you took this space, you had your G bundle on it, and you introduced a connection, a principal connection only along the S1 directions, then you could take the holonomy around the identity element of S1 pointwise in N. For every point in N, you could look at its fiber, look at its holonomy, and that would give you an actual element of G. And so what you would end up getting would be a map from N to G mod mod G, and not the homotopy orbit space. So that would be a slight enrichment. All right. So what I want to do is to study this guy here. So I'll study both of them at the same time by first looking at their honest orbits. So what does this mean? This just means I'm taking the G action on G by conjugation, and here I'm just crossing with EG and then taking that. So note G mod mod G maps to G mod G. So this is orbits. It's just the orbits. It's like it's a horrible thing to do, but just take the quotient. Just take the G action on G and just take the adjoint quotient. The same thing happens for, I mean, you could, it doesn't matter because you can always quotient kill this whole space out to get a map to this. So both of these guys, the homotopy orbits and the actual stack, they both map to this space. So let's just study this space here for a moment. So the picture for that space is something familiar to a lot of people, but it's worth just spelling it out. Of what the orbit space is. Now, G is a compact connected Lie group. So standard fact says every element of the group is conjugate to an element of the maximal torus. So conjugate an element of T, and you know, you can have identifications of these elements in T furthermore, and those are by the Weil group. So G mod G is in fact equal to T mod W. And I remind you what W was Ng of T mod T. It's the normalizer of force mod torus. It's T mod W. It's a compact space that's just T mod the W. Now, instead of studying T mod W, let's consider exponential map. That goes from H to T, and that's clearly equivariant to spectra W. So here, H is just a Lie algebra of T. So this guy here actually surjects onto this guy. You want to know what's the structure here? When everybody who has studied a little bit of Lie theory knows the structure of this, it's known as the Weil chamber. So H mod W equivalent to, so what is it? So if your Lie group was UN, this would be Rn. This would be isomorphic to Rn. It's a Lie algebra of an n-dimensional torus. It's Rn, and this would be the symmetric group. So what I'm saying is you take a symmetric group action on Rn, and that action is generated by n-1 reflections about hyperplanes. So if you work out what that does, it gives you a picture like this. So this is what H mod W looks like. Set of equivalence classes is going to be a cone. It's called the Weil chamber. And you can write down the walls of these cones as certain roots. Alpha 1 equals 0 and alpha 2 equals 0. And these are the roots we talked about in the very first lecture. There were these hyperplanes, except I'm not complexifying these hyperplanes. These are now real hyperplanes, corresponding to the non-trivial weights of the T action of the Lie algebra of the group. And to find the walls, you actually have to only look at a certain subset of roots called the simple root. So the alpha i's are simple roots. So I won't go into what simple roots are, but it's a subcollection of all roots that somehow, in a sense, generate all the roots. And those form the walls of this chamber. So this is my object here. And that maps to this. Now, this was the quotient, the honest quotient of G by the conjugation action. So what I could do is ask for what the fibers of our map, the fibers. So, right, I mean, this is an honest quotient, but the group G also maps to this, right? There's a map from G to its honest quotient, and the fibers have symmetries. Because I've taken the quotient by all of G, you can pull back that stack and ask what happens over this guy? What does it look like? So let me draw what that looks like. So G mod G, or so I'll sort of draw this picture. So here's the picture. So over the wall, alpha 1 equals 0. If you look at the stack, if you restrict the stack, then it's equivalent to just a homogeneous space of G by this group G1. If you remember GIs with these 2 by 2 guys here, in this picture at least, you just get a homogeneous space. In other words, the G action on this thing has a stabilizer that's constant throughout, and that stabilizer is G1. And then the group acts transitively on this guy. Over here, you get G mod G2, and then you have this structure here. And generically, what you will have is G mod T, again, with a G action. So these are regular elements that have a generic action. Now, I've drawn these with 4-dimensional 1 walls. Of course, in higher rank, meaning if I had the rank of the torus was larger than 2, you have these walls meeting, and in that case, you would have subgroups generated by the corresponding Gs. And those would not be ones we have considered, but they exist. They are groups that you get by generating, but it's a subgroup of G you get by taking G1 and G2, or the walls that come together will generate a bigger group. So here, generically, there's only T symmetry. You go hit this wall, you get G2 symmetry, hit this wall, you have G1 symmetry. If the walls were to come together, the symmetry would jump. And then, of course, there's a cone point where there's everything, this is a zero element. Of course, the whole group fixes it. So the symmetry here is all of G. So this is like point mod. Okay, so now I want to get to, so we call our space is Li. So I was a multi-index. So this was a space Li. Now with this multi-index, what I could do is I could inscribe a circle in H mod W. So given I, inscribe a circle in H mod W so that so here's a circle. It's coming and hitting this wall, going back to X2. This wall corresponds to this. Then it goes around, hits this wall, comes back to this point. So this data that I'm giving you has only something to do with I. There's nothing, this is a completely combinatorial piece of information I've given you. I have just told you how to inscribe a circle in H mod W by saying where the marked points, how the marked points are going to map in here. They're going to map in such a way that as you move from one marked point to another, you're supposed to hit this wall, come back, hit the wall, hit another wall, come back. And the sequence in which you hit the walls is precisely the sequence. Okay. This is this map is in the honest quotient G mod G by the conjugation action. So I can ask what happens. Can I restrict my stack over this? Can I restrict my action over this map? And you can certainly do that. When you do that, you get Li. So easy exercise. It's almost by construction. Li is equivalent to the pullback along this map. So I said that incorrectly. L sub I. So you have so the space of these sections is precisely Li. These are maps from a circle lifting this prescribed map that I just gave you. Let's call that F sub I. It's easy to see because essentially you're taking homotopy pullbacks for all segments. You look at the structure here, you will see that you will recover the pictures that I had in the second lecture.
Is Fi this circle?
Fi is the map from the circle into H mod W.
This
I just
stripes.
drew that here. That's the circle. All right. Okay, so all right, let's do some PQFT. So what is this? What I've just drawn is these so Li is G mod G background fields on S1. That's what it is. I've just given you a prescription to give you G mod G background fields on S1, right? Is that making sense? Right, because the target here is G mod G, and I'm giving you map from S1 into G mod G according to this prescription. So these are G mod mod G fields on S1. Of course, I can unravel the structure I had before to say these are G fields. On T2, which is S1 process. So, all right. So now let's do construct a TQFT out of this information. And it's going to be, to start off with, a sort of an invertible TQFT over background fields. So let Cobb n point mod mod G H be the infinity n cobordism category of manifolds with G background. So these are manifolds endowed with a map to BG. So that's all. It's a cobordism category of manifolds with maps to a space, and that space is BG. Okay, so let's take let H be a commutative global cohomology theory. Commutative is it's a cohomology theory. Commutative is straightforward. It isn't a clear meaning to what a commutative cohomology theory is. In the world of homotopy, you would say it's E infinity. What does global cohomology mean? Global has a very precise meaning, but essentially what it means is you can think of H as being equivariant with respect to any Lie group you want in a unique way. What does that mean? So imagine you had some compact Lie group, then there's underlying such a global cohomology theory, there's an G equivariant cohomology theory. And if H were a subgroup of G, you could restrict to get an H equivariant cohomology theory, but it didn't matter how you included H inside G. There could be many different ways of putting H inside G, you would get the same theory. So the theory doesn't care of how H includes into G. So it's compatible under all inclusion. There's a unique way to make H equivariant cohomology with respect to all compact Lie groups. So examples of such are K-theory, singular cohomology. So these are all examples, and there's a whole book by Stefan Schrader about what such a thing, what it is, what's the structure. So I want such a thing because, you know, the stacks we get will have all kinds of stabilizers and isotropies, and you'd have to restrict along all kinds of things. There's no global quotient that you can talk about. So the right object to study is these kinds of global cohomology theories if you want to evaluate. So now let Cn be the category of En minus 1 algebras in H modules. So in fact, the category of H modules is symmetric monoidal. It could be de-looped as many times as you want, but here I'm just taking the category of En minus 1 algebras in H modules. The unit here is H itself, thought of as En minus 1 algebra. And I have a functor. It's not a terribly interesting functor. This functor just sends point mod mod G to H. Factorization homology extends this functor to all manifolds, save maybe the top dimensional manifold. So you could go all the way up to all, but so you go up to N minus 1 dimensions using this association. Okay. What I want,
Not the trivial theory.
it's trivial pointwise, but it has backgrounds. So it's an invertible theory over the background fields. So it's sort of like a line bundle over backgrounds. So that's a crucial observation here, but I compactify it on S1. So i.e. I consider M of the type that we talked about before. And what I get is Cobb N minus 1 from G mod mod GH into Cn minus 1. And this sends G mod mod G, so the value of a point over to, again, H. Maybe I should decorate this H by saying this is an En minus 1 algebra. This is N minus 2 algebra. I should say cross G mod mod G. So what I'm doing is, what are objects here? They're manifolds with a map. So for every manifold with a map, I will give you its partition function, right? So what you end up getting would be a family of objects in this guy parametrized over your maps, the collection of maps, where the fiber is the actual value, the partition function of your manifold. So for a point, this is what I get. And in fact, it's an invertible theory. So every time you're just going to get a copy of H, but the copy of H varies non-trivially in terms of G. It's an equivariant object, right? The G actually acts on this guy. Remember, there's an underlying G theory here. So it's a non-trivial bundle, but each fiber is trivial. It's just H. All right. So I am minus 1 minute. So let's trace this functor on S1 along Li. So over Li, we get the H bundle. Because this is background fields on a circle over S1. So remember, I told you that I can give backgrounds on S1. LIs are backgrounds on S1. So it's a decoration. It's a configuration space of G mod mod G background fields. So this is what you would get if you did it over the circle, right? So this, like Dan pointed out, is an invertible theory, meaning the fiber over each point is just H, but of course it varies non-trivially with G. So what I can do next is gauge it, take global sections. So it's a line bundle, so I'll take global sections of it. If I take G equivariant global sections of this, what do I get? So I get the object. This is isomorphic to the Hochschild homology of, right? Now, clearly the LJ sits inside Li, so these bundles restrict under transparent defects, meaning under maps here that you can push off the edge. So LJ, for instance, would be a map that you prescribe, but it doesn't hit this. It sort of just goes around and doesn't hit that wall. So LJ will sit inside Li, then you will have restrictions. So this ends up giving you the complex Kovanov's complex. Now let's look just briefly, I'll say in words what the twisted situation is. The twisted situation ends up giving you a complex of modules over H. So that doesn't fit in this framework. The way to make this fit in this framework is to start off with n equals 4, construct this theory in 4 dimensions, and then put the theory that you actually want, the twisted theory, on the boundary. Because what you get would be a module. You get a module. This twisted theory is a module over something like this. It's a module of a theory like this. But itself, it is not an algebra or anything like that. So what it naturally wants to, the place where it naturally wants to sit is on the boundary of something. And if you get the dimensions right, it's a module. So it's not an algebra. The dimensions ask the 4-dimensional theory to give you an E1 algebra in the bulk. And on the boundary, you should get a module. That's your twisted theory. So the Kovanov-Rosansky SLN is 3D theory on the boundary of 4D theory of the form above. So the ones we've constructed here would have to live in the bulk of the 4D theory. So remember, all I've done is agnostic with respect to n. So I could set n to be 4, construct this theory for n equals 4, and then you get a 3D theory on the boundary of it. That's the kind of theory, that's the twisted theory. Anyway, I'll stop here, sorry.
I suspect there'll be a bunch of questions. Maybe we can ask them during the chaos of setting up for the gong show.
Sorry for going over.